This video will be for Module 1, Part 4, and will include the Parolee Discrimination Example. All right, let's go ahead and get started then. This example came from an article published by Surgery and Fairley. And this case study is entitled Greenholz versus the Nebraska Penal and Correctional Complex. The reason I'm going to use this example is because they actually provided the data for this example in that article. And that data is provided here in this table. So you can see we have a breakout of the race and ethnicities for white, African American, Native American, or Mexican Americans. We have the individuals that were eligible for parole. So here a value of 590 simply indicates that there were 590 whites that were eligible for parole during the time of this study. We also have the number that were paroled. So over here on the right, we have 358 whites that were eligible for parole during the time of this study. So let us consider the initial analysis that was done by the courts. And in particular, I'm going to point out this sentence that was provided in that initial court ruling. So they say, for example, the court noted that 65.4% of the 902 inmates eligible for parole were white. So how that value was computed is they just took and summed up the number of individuals that were eligible for parole, so the 590, 235, 59, and 18, and they got 902. They took the 590 individuals that were white and divided by that 902 and determined that it was about 65%, 65.4%. So of the individuals that were eligible for parole, 65% of those were white. They then looked at how many whites received parole. So they did that same thing over here with the right-hand column. They took the 358 plus the 148 plus the 24 plus the 5. There's 535 individuals that got parole. How many or what proportion of those were white? They took the 358 and divided by 535. And here they're saying they got 66.9%. So they compared that 65.4%, which was the individuals eligible for parole, how many of those were white, and noted that it was pretty close to the proportion of whites that were paroled, which was the 66.9%. They went on to say that that was a difference of only about 1.5%. They also argued that the corresponding percentage disparities for African Americans, Native Americans, and Mexican Americans were in each case 2% or less. The court determined that a value of 2% or less was an insignificant difference. I'm going to argue from a statistical perspective that that logic is flawed. To help communicate that, let us consider the fact that 18 of the 902 individuals were Mexican Americans. So if we go back up to that table, we can see that 18 of the 902 eligible for parole were Mexican Americans. 18 divided by 902 is right at 2%. So what that means is that the Nebraska Penal and Correctional Complex could deny parole to all Mexican Americans. So if they denied parole to all Mexican Americans, then that would indicate, I guess that proportion would be 0% received parole. 2% eligible and 0% that actually received parole. That difference is 2% or less, which the court said up above that was insignificant. So in other words, the state of Nebraska would never be found guilty of discrimination for the Mexican Americans. So simply choosing an arbitrary value of 2% and saying that's close enough is not going to work very well in general. So how would we approach this from a simulation-based approach? Or what would a statistical analysis look like, or a statistical evaluation? Well, we're going to set up a simulation model under a situation of no discrimination. So let us consider how many individuals received parole when race wasn't part of the equation. There were a total of 902 individuals that were eligible for parole, and 535 of those received parole. So if we look at this kind of in two buckets, there were a total of 902 individuals, 535 received parole, and 367 did not. And these numbers, again, are obtained across all races. So what proportion of the individuals received parole? To compute that, I would just take the 535 and divide by the 902, and that's 59.3%. So this 59.3%, again, was computed across all races, and hence will serve as a benchmark for what we'd expect to happen if race or ethnicity were irrelevant to whether or not an individual received parole. We're going to use that quantity now in our simulation model. So here, we're going to consider the Native Americans. So for each individual trial, in the context of this example, is going to represent a Native American. There were a total of 59 Native Americans eligible for parole. Therefore, our simulation study is going to consist of 59 trials. The simulation study will be set up under a no discrimination or a all things fair situation. And the proportion of inmates that received parole under that no discrimination or all things fair situation was that 59.3%. So again, the necessary quantities for my simulation study are going to be the number of trials, which is just going to indicate the number eligible for parole. That was 59. And then the chance or likelihood of parole under a fair situation is going to be that 59.3%. We now have the values necessary to compute the expected quantity. The expected quantity is just the number of trials times that proportion up above, or that percentage. So I'm just going to take 59 times 0.593 here, which turns out to be 34.99, or about 35. So under an all things fair situation, I would expect to see about 35 Native Americans being paroled. So a depiction of my simulation model is going to look like this. Again, what I'm tracking here is the number of Native Americans paroled. It's going to range from 0 up to 59. Under a no discrimination situation, I should be 59.3% of the way up that number line. And again, that center of that distribution or that pyramid is going to be right here at 35. And again, my simulation model is going to try to mimic a no discrimination situation. I've mentioned this before, but an important element of the simulation model is to gain an understanding or a measure of that inherent variation that exists in our simulation. So this particular picture, that inherent variation goes to about 27, 28, and up to about 43 or so. I don't know, without running that simulation, how much inherent variation exists. So I might end up with a distribution that's much wider than that. It might go, this particular distribution goes all the way down to 20 and all the way up past 50. Part of the goal of the simulation study is to figure out whether or not I'm in this situation here, or do I have more inherent variation like I've shown here. The other thing that I need to worry about in my simulation study is what end of the distribution do I care about? In this particular case, I care about the left side of this distribution or this picture. The left side is going to indicate that too few Native Americans were paroled, and that'll indicate discrimination. So certainly if no Native Americans were paroled, okay, there should have been about 35 paroled, but if no Native Americans were paroled, then that's going to indicate discrimination taking place, or is likely to indicate discrimination is taking place. So the left side of this distribution is of interest here. So this table here just provides a recap of the various quantities that are relevant for our simulation model. Again, the lowest possible value is going to be 0, and the largest possible value here is going to be 59. In these examples in Module 1 and in Module 2, we're going to be simply counting up quantities. So before we were counting up the number of correct. Here we're counting up the number that received parole. So that number line is going to start at 0 in these first couple of modules. The label here is just the number of Native Americans that were paroled. The expected value is 35. We talked about how that was computed up above. The side that I care about is the left side of this picture, or the left side of that graph. And again, that is because I want to know whether or not 24 is too few, because too few would indicate discrimination. And then the study outcome there is just 24, the number that actually received parole. Let's just step back and take a big picture here of what we hope to accomplish with our simulation model. So the question that we're trying to answer here is, does 24 Native Americans paroled out of the 59 provide enough statistical evidence to suggest discrimination was taking place against Native Americans during the time of this study? What we're going to gain from that simulation is a determination of whether or not 24 is an outlier against that no discrimination situation. Talk a little bit about how we could obtain the outcomes. Let me hit refresh here. There we go. Let's talk about how to obtain these outcomes. So from the simulation model. Again, we can use our 2AFC app that I created, which that link is provided there. And the way that we're going to set that up is just shown here. The first outcome is whether or not an individual was paroled, either yes or no, would be the two outcomes. And then their associated probabilities, again under a no discrimination situation. The sample size here is going to be 59. Let me just go over to that app and show you how to put those in and run a couple of these. So paroled yes, that proportion should be 59.3%. And you're going to want to put that in as a decimal as shown. Paroled no. So that's just going to be 1 minus that 59.3%, which is 0.407. And then the sample size is just the number of trials. That's going to be set to 59 here. So those are my two outcomes, whether or not an individual was paroled, and then the associated probabilities under a no discrimination situation. So you can see here that the simulation app runs one set of those 59. So that first Native American, received parole. That's what that indicates. The second received parole. The eighth one did not receive parole. And then that tally there just records how many individuals received parole. So 43 did here and the 16 did not. If we run another trial, see that I got 36 here. Now these values here should be around 35. So there's a 31, a 30, a 39, 38. Okay, so the expected quantity here should be 35. So these values should be around 35. We actually call these quantities a statistic. A statistic is just some summary measure that I get from data. So that 35 is actually a statistic that I want to keep track of as I go through these simulations. Let's go back to the notes then. So I provided, looks like 4 different simulated outcomes here. I got a 38 and a 33, a 27 and a 35. And I could just keep doing that many, many times if I wanted. There on the screen is the definition of a statistic. Again, that's just a summary measurement computed from the data. And the summary that I'm computing here is just trying to keep track of how many people received parole. I guess another statistic would be the number of people that did not receive parole, but I only need to keep track of one of those here. So if I know that 38 received parole, then I know that 21 did not, because I have a total of 59 individuals here. So it's only necessary to keep track of one of those quantities. And here I'm going to keep track of the number that received parole. So let us consider 3 graphs. Graph A was the graph that I obtained over my 10 repeated simulations. Graph B was just 10 repeated simulations from some other person. And then graph C was just yet another person that received their 10 simulated outcomes. I'll just take a moment here and let you answer these questions that are on the screen. So go ahead and hit pause and provide an answer to these questions. Okay, let me talk a little bit about number 3 here. It appears that when only 10 repeated outcomes are used, the value that would be used to separate the likely from the unlikely values would vary somewhat from person to person. So that makes it hard when determining whether or not 24 is going to be an outlier. So what we're talking about here in part graph A is that the edge of the graph appears to be at about 27. In graph B, the edge of the graph is 31. In graph C, the edge of the graph is at 30. When I don't have very many simulated outcomes, it's kind of hard to determine where the edge of that graph is at. Again, that is important because I'm trying to determine whether or not 24 is too few in this picture. And if I don't have a good understanding of where the edge of the graph is, that makes it difficult to determine whether or not 24 is too few. So certainly in graph B, 24 looks like it's a long ways from the edge of the graph. So that might indicate that 24 is an outlier. However, in graph A, 24 is not that far from the edge of the graph, so we might not be sure of whether or not that's an outlier. So a graph based on many simulated outcomes is better than a graph that's based on only a few simulated outcomes. Now this is especially true when interest lies in determining an appropriate cutoff value that will be used to separate the likely from unlikely values. So again, that cutoff value is on the edge of that picture or on the edge of that distribution where I don't have very many outcomes. So it's important to get many simulated outcomes in order to determine where that lower cutoff is at. So here in this graph, I got 100 simulated outcomes. It looks like the lower edge of that graph is maybe 24, 25, 26, maybe 27 here. If I add another 100, so this picture right here has a total of 200 simulated outcomes on it, we can start to see that 27 is occurring somewhat often relative to the values of 25 and 26. So 25 only occurred once out of the 200, 26 occurred twice out of the 200, but 27 occurred 5 times out of the 200. So certainly 27 is occurring somewhat more frequently than 25 or 26. So I'd say the edge of this graph is right here around 24, 25, or 26. If I added, let's see here, I added another 150. So now I'm up to 350 repeated outcomes on this graph. Starting to get quite a few dots there. But here you can start to see that the edge of the graph seems to be settling down right here at 25. So again, 26 has 3 outcomes, whereas 25 has only occurred once, and out of those, whatever it was, 350 repeated outcomes here. So we're getting a better understanding of where that edge of that graph is when I get more and more outcomes. So just some comments here. Notice that the outcomes appear to be centered around 35 on each of these graphs. So consider the one with 100 dots on it. The graph tends to be centered right at about 35. With 200, the graph centered about 35. And even with 350, that graph is centered around 35. Another thing that I'll point out is that some of these anomalies that occur when I don't have very many simulated outcomes. So for example, 35 is supposed to be 35 is the expected outcome and should be occurring most often. However, you can see out of these 100 dots, 36 was the value that actually occurred more often. When I did 200 dots, it looks like 33 actually occurred somewhat often. But as you do more and more simulated outcomes, some of these anomalies are going to start being reduced. So here with 350 simulated outcomes, you can see that 35, the expected outcome, is actually occurring more frequently. Also, with several hundred repeated outcomes, it becomes easier to determine an appropriate cutoff on that left edge of that graph. I already talked about that a moment ago. All right, so let's next consider the following sets of graphs. And I've just generically labeled them graph A through graph D. In graph A, I only had 10 outcomes. simulated outcomes. In graph B, I did 100. Graph C, I ended up creating 1,000. And then in graph D, I ended up creating 10,000. So I'll give you a moment here to answer the questions. There's 4 questions here, I believe. So go ahead and hit pause on the video and try to attempt to answer these 4 questions. Okay, real quickly, similarities that exist. Again, we've already talked about those, but these graphs are centered around 35. The graphs tend to settle down in similar spots. How many repeated outcomes are necessary so that anomalies in these distributions are negligible? I'd say after about, so there's 10, certainly is not enough. After 1,000, we're starting to get a pretty good picture of what's going on, but again, we have some small anomalies here. Certainly after 10,000, it looks like those anomalies are pretty much gone after 10,000 repeated outcomes. You might notice that looks very much like a bell curve, and we'll have more discussion about that later on. I do want to talk about question 7 here. A friend suggests that the following rule for determining an outlier. Any value lower than the smallest value on the graph would be considered an outlier. Now, this rule is not going to work very well when I have tens of thousands of simulated outcomes. So let's go back up here and look at the difference between maybe 100 simulated outcomes versus 1,000 versus 10,000. So what your friend is proposing is that anything that is lower than the smallest value on the graph is going to be an outlier. So if I use this picture right here with 100, that rule would say that 24 and anything less than 24 would be an outlier. But if I use 1,000 observations, then I'd have to change that rule to 21 or anything less than 21 would be considered an outlier. If I use the 10,000 outcomes, then I'd have to use anything that's 20 or less to be considered an outlier. Now the problem with that is as more and more outcomes are obtained, my cutoff value or my value that I'm determining or the value that I'm using for determining whether or not I'm an outlier is changing. And in fact, if I get 100 bazillion gazillion outcomes, it's very possible that I'm going to get values way down here at maybe 10 or 5 or potentially even at 0. And if I use that rule that anything less than that is going to indicate discrimination, well, I'm never going to indicate discrimination. If my smallest value on my graph, if I actually get one under no discrimination situation at 0, then I would never indicate that discrimination was taking place. So again, the important thing here is to separate the likely from the unlikely outcomes. So I would say that even though I had a value of 21 and 22, those are still somewhat unlikely in this situation. I believe I only got 1 dot there at 21 and 1 dot here at 22, so that's not very common. Out of 10,000 outcomes, I only got 1 dot down here at 21 and 22. So those are still unlikely outcomes. So let's talk about evaluating evidence here, or making a decision for the case that we're presented with here. And we're going to use graph C. That's the graph based on 1,000 outcomes. So the number of dots that are at 22, I just had 1 dot here at 22. I had 1 dot at 23. I have 2 dots at 24. Kind of hard to see that, but there's 2 dots there and 3 dots there at 25. Now my study outcome here is at 24. Okay, so I'll let you answer the final 3 questions here that are provided on the bottom of this page. Okay. So again, the idea of this is to try to determine whether or not 24, the study outcome is a likely or unlikely value. And as I've stated, I believe that 24 would be an unlikely value under a situation of no discrimination. It does sit in amongst these dots, but it's still an unlikely outcome. So I would have evidence for discrimination. So from a statistical perspective, I would say that a value of 24 provides evidence for discrimination. So from a statistical approach, I would say that the Nebraska Penal and Correctional Complex were indeed discriminating against Native Americans regarding parole during the time of this study. Okay, that does it for this video. Thank you.